Welcome to The Explainer. Today, we are diving into a concept that sounds like it's straight out of a science fiction movie, but it's a very real part of how our universe works, and it's being proven all around us every single day. We're talking about time dilation.
So, let's just jump right in with the big one, shall we? Is time travel actually possible? I mean, forget what you've seen in the movies for a second, and let's think about the actual science.
And the answer is yes. And it's all thanks to this thing called time dilation. The whole idea here is that time isn't some universal clock just ticking away at the same rate for everyone and everything. It's actually relative. It can literally stretch and shrink.
Okay, so how is that even possible? How can time itself bend? Well, it turns out it's because something else in the universe is incredibly stubborn. It absolutely refuses to change. And this one unbreakable rule is the key to everything.
To really get our heads around this, let's do a little thought experiment. Just picture yourself on a train that's moving at a ridiculous speed. You're inside, holding a normal flashlight.
All right, so you flick it on, a beam of light shoots out. Now, if you had some crazy advanced gear with you, you could measure the speed of that light beam from your point of view on the moving train. Now, here is where reality just gets weird. Let's say your friend is standing on the platform outside as your train zooms past. They also measure the speed of that light beam from your flashlight. Now, common sense would tell us that they should measure the speed of your light plus the speed of the train, right? But they don't. They measure the exact same speed that you do. And why is that? It's because light, well, it kind of plays by its own rules. This slide nails it. It's almost like light itself is saying, look, I always travel at 300,000 kilometers per second, period. I don't care how fast you're going or where you are. It's the universe's ultimate non-negotiable speed limit.
So think about it. If the speed of light absolutely cannot change for anyone, no matter what, something else has to give. And that something is time. So let's look at the two main ways this incredible effect actually happens.
Just as Einstein figured out, there are two sides to this coin. On one hand, you've got time dilation from speed. The faster you move through space, the slower time passes for you. And on the other hand, there's dilation from gravity. The stronger the gravity you're experiencing, the slower time passes for you.
Let's tackle that speed part first with a super simple story. Imagine two kids. Let's call them Kid A and Kid B. Kid A just stays here on Earth, living a normal life. But Kid B gets to go on an amazing trip, hopping on a rocket and zipping around the galaxy at nearly the speed of light.
So Kid B eventually comes back to Earth. And here's the mind-blowing part. When they return, Kid B will be physically younger than Kid A. And this isn't a storytelling trick. For Kid B, time itself, their biological clock, everything, literally ran slower because of how fast they were moving compared to Earth. This chart here really drives the point home. This isn't some tiny, unnoticeable effect at these speeds. For every full year that passes for Kid A back on Earth, only about 0.8 years. So what? A little over 9.5 months would have passed for Kid B on that spaceship. It's wild.
Okay, but speed is only half of the puzzle. The other big piece is gravity. Einstein's theory of general relativity tells us that massive objects, like planets and stars, actually create a dip, or a curve, in the fabric of space and time. And the deeper you are inside that curve, that gravitational field, the slower time moves.
And we're not just talking about extreme things like black holes. This happens right here, right now. Because gravity gets a tiny bit weaker the further you are from the center of the Earth, time is literally passing a tiny fraction of a second faster for someone on top of a mountain than it is for someone down at sea level.
Now, I know what you might be thinking. This is all super interesting, kind of brain-melty physics, but does it really matter in our everyday lives? The answer is a huge yes. In fact, you probably have proof of this whole wild theory sitting right in your pocket.
I am, of course, talking about GPS, the navigation on your phone. Without constantly correcting for time dilation, the entire GPS network would be completely useless, and it all hinges on one little number.
38.
That's 38 microseconds. It sounds like an insanely small amount of time, right? But that's how much the clocks on GPS satellites would be wrong every single day if the engineers just ignored Einstein's theories.
And here's what's so fascinating. The GPS satellites are getting hit by both kinds of time dilation at once. Their incredible speed as they orbit the Earth is trying to slow their clocks down. But because they're so far away from Earth, where gravity is weaker, their clocks are also trying to speed up. When you do all the math, the net result of this cosmic tug-of-war is that their clocks run faster than ours by exactly 38 microseconds a day. If we didn't correct for that, your GPS would be off by miles within a day.
So, what's the big picture here? What is the major takeaway from all of this? What does time dilation really tell us about the universe and our place in it?
If you only remember one thing from this, let it be this: there is no universal now. Time isn't some giant river flowing at the same speed for everyone. It's a flexible, personal dimension. It's entirely relative to how fast you're moving and where you are. Your time is literally not the same as my time.
And that leaves us with a final, really profound question to chew on. If something we think of as being so fundamental, so constant, as time itself is actually this flexible, well, what other parts of our reality might not be nearly as solid as they seem?